let's talk about tablet testing with regards to compaction force and hardness. So here we've got example tablets that we made earlier with 4 different compaction forces. Normally, I don't label my tablets with a compaction force. Instead, I would do 10 or 20 tablets, all of one force, and then repeat as needed for all my compaction forces. But for the purposes of demonstration here, so I'm going to load all of these, and this device can measure weight, tablet thickness, which you maybe can tell changes as the compaction force goes up, but then also the diameter of the tablets, and then finally the breaking force of the tablets. I've got the tableting results here. So first, if we take a look at our diameter, in fact, there's really no change for any of the compaction forces. Our material's not particularly elastic, so this diameter is set mostly by the hole in the die. So that's just 13 millimeters. Likewise, weight is set primarily by both the die diameter and the fill depth. And for this material, which was relatively free-flowing, there was not too much change, maybe from 400 milligrams up to maybe 406 milligrams. Now, when we look at the thickness, we start to see some real changes. So for the 2 kilonewton, we had 4.1 millimeters thick tablets, which then, with the increased force of 5 kilonewtons, we got 3.1 millimeters. At 7 kilonewtons, they were compressed further to 2.9 millimeters. And then at 10 kilonewtons of force, they were compressed all the way down to about 2.6 millimeters. Finally, let's take a look at our hardness values. Here, initial results were about 37 newtons of breaking force. The next level of compaction force, we had about 96 newtons. At 7 kilonewtons of compaction force, this increased again to about 144 newtons. And finally, at our highest compaction force of 10 kilonewtons, we got about 224 newtons of breaking force on these tablets. So earlier, we made tablets with different compaction forces and measured their properties. Now let's take a look what we do with that data. So you see here a curve that the pharmacopoeia refers to as manufacturability, where we're plotting our tablet crushing force against the compaction force that was used to create those tablets. You can also use the tablet shape, diameter, and hardness to calculate the tensile strength of your tablets. In that case, you're going to want to also use the area to convert compaction force into compaction pressure, and that would be a graph referred to in the pharmacopoeia as tabletability. For our purposes here, we can show with just the direct measurements that we were taking in the lab. So here you can see MCASL 90, and you can see that it has a really nice linear response of increasing tablet hardness with increasing compaction force. So here, if you're targeting a specific tablet hardness for your application, you can say, I want 200 newtons of tablet hardness. Let's see, that's maybe about 9 kilonewtons of compaction force, and you can target your hardness that way. Now let's take a look at how some other materials respond in manufacturability. First, let's take a look at the same size of material, but actually silicified microcrystalline cellulose rather than the non-silicified version. And here you can see that you also have a fairly linear response of hardness to compaction force, but actually your tablets at any single compaction force are a lot harder. So this shows that there's even a little more compactability in the silicified version of microcrystalline cellulose than in the standard. Now let's take a look at a filler that is often used to improve flowability. And here you can see we refer to M-compress as a filler and MCC or SMCC as a filler binder, because here the M-compress, it may have helped some flowability because of its high density and flow properties, but it's really not contributing to the tablet hardness. Finally, let's take a look at MDEX. So this material is actually quite nice. It had excellent flowability, and here you can see that it has a nice response where you can get good tablet hardness as you increase compaction force. So if instead of taking a compaction force and looking at the difference in tablet hardness, you choose a tablet crushing force and you look at the amount of compaction required to hit that target value, you can see that with the SMCC, maybe 3 kilonewtons is sufficient to hit that target hardness, whereas for MCC, you need 5, MDEX, you need a little more than 6, and actually you never achieve it with M-compress alone. So this has a couple of advantages. One is If you can compact hard tablets at a lower compaction force, you actually put less stress on your tablet press and the dies, tooling, etc. So there will be less wear on the equipment. But then also, because it doesn't need to be compacted quite so far, you actually have increased porosity, and that's going to improve your disintegration performance as water is more easily able to get into the pores between the particles and break that tablet apart.
In the next episode of JRS Tableting Studio, we begin our series on powder flowability. See how powder flow through different orifice sizes can be used to characterize flow behavior, and why good flow properties are essential for consistent dosing, stable tablet weight, and reliable content uniformity. JRS Tableting Studio. Stay tuned.